All right, everyone, I've been told to commence. So hello and welcome everyone to this webinar today, wherever you may be in the world. Thank you for joining us. I'm Johannes from DHI in Australia. Thank you for setting aside the time to be with us here today. So our webinar topic today is an introduction to fully integrated watershed hydrology modeling using Mike Shee. The webinar will give you an overview of the current state of hydrology modeling, demonstrate why an integrated approach is important, address the myth that integrated modeling is too complex, and show how integrated modeling can be easily incorporated into your modeling activities. Mike Shee is typically used for impact studies for changes in land use and climate, surface water impact from groundwater withdrawal, watershed water balances, conjunctive use of groundwater and surface water, wetland management and restoration, and river basin management and planning. Today, our presenter is Patrick Delaney, President of DHI in Canada. Patrick is involved in all aspects of DHI Canada's business, including consulting services, software sales, technical support, and training. Patrick is primarily involved in projects related to integrated water resources management, urban and riverine flooding, wastewater collection systems, and groundwater modeling. He has more than 20 years of experience in the development and application of water modeling software tools and technologies, and he has successfully managed the execution and delivery of complex interdisciplinary water management projects. Patrick has led many professional training classes for groundwater modeling, integrated watershed modeling, urban flood modeling, and river system flooding. Patrick has also advised many clients working on local, regional, national, and international projects.
Well, thanks, folks. I appreciate the opportunity to give this presentation, and it looks like we have a really good turnout, so I'll try to make it as entertaining as possible and informative, maybe a little bit too. So if you're not already familiar with DHI, we are an independent self-governing research and consultancy organization. It's a not-for-profit organization. The mandate to build competence and promote technological developments relevant to water and environments. We have ongoing activities related to software sales and consulting projects worldwide, and a total staff of about 11 or 1,200 now. I gotta say, we do a lot of consulting work, but we're also probably best known for the range or the family of software products that DHI developed related to water modeling. So this is showing a kind of a graphic of the range of software products that DHI is involved in the development and support training. So we have the Mike products, I guess, and so it kind of all started in the marine sector, where we were developing software, and we had physical labs and doing evaluations of different setups, and decided to it was a lot more efficient to develop numerical models and set up all these physical models. We still do a bit of both, though. So we have coastal products here in the top left-hand corner: BlitPack, Mike 21, and Mike 3. And then we have water resources products. We call them water resources. They deal with inland water. So Mike Flood, Mike Shee, Free Flow, Mike 11, and Mike Basin. And then we have kind of city water modeling products, Mike Urban, which deals with stormwater and wastewater collection systems, as well as water distribution systems. And then West for wastewater treatment plant processes. So for today's topic, we're going to talk about integrated watershed hydrology modeling. And so what is integrated watershed hydrology modeling? If you look it up in Oxford or Webster's Dictionary, I'm pretty sure you won't find a definition there. And many people probably think of it as many different ways. But here at DHI, and in the context of today's talk, integrated watershed hydrology modeling is the ability to represent the different phases of the hydrologic cycle, the land phases of the hydrologic cycle, in an integrated, dynamic, and continuous way. So if we look at the kind of the typical representation of a watershed, we have all these different processes. We have rainfall and precipitation, possibly snow melt and accumulation, although probably not so much of that in Australia. Infiltration into the subsurface, runoff into rivers and creeks and lakes and whatnot, and evapotranspiration. So all these processes, they all kind of work together to represent the hydrologic cycle, and water doesn't really know much about these different processes or representations of it, whether it's river hydraulics or rainfall runoff of the surface or groundwater flow. It's just going where it's going to go. And so we have pretty good understanding of a lot of these different processes, but the concept or the possibility of physically representing these processes in an integrated model is something that the hydrologists have been salivating over for many years, going all the way back to 1969, where Fries and Harland kind of outlined that blueprint for a physically based, digitally simulated hydrologic response model. And that's kind of where things took off for DHI. So back in 1969, I mean, they looked at, you know, what were the barriers for this integrated physically based system, and was it science? Even back then, the processes of unsaturated flow, groundwater, saturated groundwater flow, rainfall runoff, and river hydraulics were fairly well understood. Didn't have as much of data available as we do these days, but even then, you know, pretty good understanding of what data was needed and what went into the models. And then computers, obviously back then there wasn't a whole lot of computing power, and we changed things a lot over the last 40 years or so, 40 or 50 years. So things have changed a lot. We have basically the science, we have an understanding of it, we have more data now than we've ever had, and we have more computational power than we've ever had to tackle these challenges. If we look at the current state of hydrology modeling, and we look at the hydrologic cycle, we have all these different processes that contribute to it. We have climate processes, surface runoff, infiltration, evapotranspiration, river hydraulics, and groundwater. And all these processes are represented in different ways. So the climate processes are obviously the main drivers of our hydrologic cycle. So we have rainfall, which is introducing precipitation and moisture into our system. Temperature, which kind of drives that transformation of that precipitation to frozen conditions or to liquid water conditions, and drives the evapotranspiration as well. And then there's solar radiation and wind that also plays a part in that evapotranspiration process. So those are the main drivers for the hydrologic cycle. And then we go to kind of the surface processes and surface runoff that are involved in the hydrologic cycle. And these are kind of what's happening on the surface. So the rain hits the surface and what happens. We have some of it that runs off and gets into our rivers and lakes and oceans. We have some that infiltrates into the subsurface and some that evapotranspirates. And there's a range of different hydrologic surface runoff models that are available. I'm not so familiar with what's the standards there in Australia, but you know, there's codes like SWIM and HMS and PRMS and HSPF, and of course the DHI software, Mike Shee and Michael Evan. They all have some component of representing surface runoff hydrology in ways that are well understood, well practiced. Engineering firms are doing hydrology studies all the time, every day. So the process is well understood, the science is well understood. It's used in an engineering capacity on a daily basis. Then we have the river hydraulics processes. And again, you know, well understood science, well understood equations, and typically St. Venant's for 1D anyways, overland flow, 1D river flow, St. Venant's equations for conservation of mass and momentum are kind of the standards. We have, again, well understood processes for developing, calibrating, and using these models for a range of activities to look at flooding and dams and dam breaks and things like that. So again, very well understood science. We use it a lot. We know the data that's needed. We know the process to build, calibrate, and utilize these models in an engineering or science-based capacity. And then we have the groundwater system. So below the surface, what's happening? We have models that are used and modeling processes that are used to represent the flow of water in the subsurface. And we have kind of a typical representation here where we have a kind of a conceptualized subsurface condition where we have a couple of different layers, maybe an aquifer, unconfined aquifer on the top, possibly a confining layer, and then a deeper confined groundwater aquifer. Some boundary conditions that control inflow from outside the model domain into the model domain, and then other boundary conditions here that can control flow out of the system. And so typically in a groundwater model, we have possibly steady state conditions if we're looking at very long-term simulations, sustainable yield of pumping wells or things like that. And so we would specify what the recharge is into that saturated groundwater system. So we have a groundwater table kind of shown here, and we say, well, we know it's going to rain, whatever the amount of rain is, 300, 400, 500 millimeters per year, and we estimate that maybe 20% of that is going to get into the ground and recharge our groundwater table. So we kind of calibrate the model by modifying the recharge and modifying the hydraulic conductivities of the groundwater system. So we achieve that balance that we want to see that gives us the groundwater levels that we are observing. So in this case, the recharge is something that we specify. It has nothing to do with anything that we've observed on the surface or any of our hydrology models. There's no implicit or explicit connection there. If we want to get a little bit more fancy with the groundwater models, we can add water levels for surface conditions. So we can represent rivers or lakes in our groundwater system, typically done using a specified water level. Because the time frames we're looking at for groundwater models, the variations in the water levels in the rivers and lakes typically doesn't have a big impact on the groundwater. It's usually the groundwater that's discharging to those river systems. And then if we want to get even a little bit more fancy, we could say, well, we don't want to specify what the recharge is to the saturated zone. We want to let the model calculate the flow through the unsaturated zone. So rather than specifying what the recharge is to the groundwater table, we're specifying what the infiltration is into the subsurface, and then we have an unsaturated zone model that calculates flow through the unsaturated zone before it gets to the saturated zone. But again, we're specifying what that infiltration rate is. It's not being calculated by any kind of model, and typically it's a calibration parameter. So we have all these processes. So we have climate inputs, we have surface runoff, infiltration and evapotranspiration, rivers and lake models for the hydraulics, and a groundwater model to look at the groundwater system. So can we say we have an integrated model? Typically no, because we don't have any sort of dynamic feedback between these systems. So we can say that we have climate, it feeds the runoff goes into the subsurface, or it evapotranspirates, or it gets into our rivers and lakes, and from our rivers and lakes we can have a hydraulic model that tells it what the water levels are and how fast it's going and what the flows are in that river system. But there is no connection to our groundwater system. There's no dynamic feedback between those surface water systems and the groundwater systems. And if we're looking at climate change, we're looking at land use changes, we need to have those feedbacks taken into consideration. So here's a couple of really simple examples of why that's important. We're looking at examples of urbanization and groundwater pumping. So in the urbanization example, we have this nice forested area here. We have a groundwater table represented below the ground surface here. So the trees are at the surface, and this blue line here is the water table below the surface. Typically, the water table follows your topographic conditions. So if we want to build some homes there, it's nice forested areas, and people want to live close to these forests, so they deforest it a bit, put up some houses, pave the surfaces, route that runoff as quickly as it can land on the properties. We want to make use of our properties, so we route that runoff off as quickly as we can. So what ends up happening is we have runoff being, used to infiltrate in these areas here is being routed as quickly as possible down to the low-lying areas here. So what ends up happening is we end up raising the water table down here because we have more infiltration in the low-lying areas, and we end up creating these high water tables and possibly wetland conditions. So we get this change in the vegetation and associated wildlife and habitat changes as well. So what used to be this nice forest is now this wetland, And these people here who bought right adjacent to the forest paid a lot more money to be there, and now they're getting all kinds of mosquitoes in their backyard because it's a wetland instead of a forest. So that's a simple example there of urbanization and how it can impact the groundwater system as well as the surface water system. Next example is groundwater pumping. And here in this example, we have a wetland area. We have a creek that's running through it. In this case here, it's a groundwater fed creek. So we have a high water table here. It's feeding the creek and keeping these moisture conditions here in the wetland such that it supports the wetland habitat. We have an aquitard here and a confined aquifer below the aquitard that has an upward gradient. So the confined aquifer is actually providing water into this unconfined aquifer, and it's feeding the streams here. So people see this and they say, well, that's a nice confined aquifer there. We can throw in a pumping well and get some water for irrigation or industrial municipal purposes or whatever it might be. But they fill a pumping well and they start pumping out of that confined aquifer. And if they pump too much out of there, what ends up happening is they depressurize the confined aquifer and you end up reversing that gradient. So now you're starting to pull water from that confined aquifer to provide water for the confined aquifer. So the gradient reverses. What used to be an upward gradient is now a downward gradient, and you're pulling water from this overlying unconfined aquifer to provide that pumping water for the confined aquifer. That has a direct result here by lowering the water table, and now you're starting to pull water from this creek rather than feeding water to the creek. And the wetland over here no longer has the moisture conditions to support that vegetation and habitat. So, of course, they're very simplified examples and idealized examples, but to kind of give you an idea of the kind of feedback and dynamic feedback and why it's important. So to measure and manage cumulative effects or integrated watersheds, the models should not be run necessarily in sequence, but they should be run together. So you need this dynamic feedback between evapotranspiration, precipitation, temperature, surface runoff. Snow accumulation and melting, maybe not so much in Australia. Infiltration, river hydraulics, and groundwater. And all these things, the water is exchanged between these continuously and dynamically. So how does that look in our models here? If we go back to the previous example I had of a groundwater system, and we look at the example I gave there where we have infiltration being a calibration parameter. So it's something that we estimate and we modify and we adjust the infiltration rates to try to get the amount of water that's going into the subsurface here to give us the water table elevations that we measure in our piezometers and monitoring wells. So rather than having that as a calibration parameter, something that we're adjusting and have no connection to any kind of other models, we put that hydrology, that surface hydrology model on top. And so no longer is that infiltration rate something that we estimate, but it's something that the model calculates based on the inputs, climate inputs. But now you have a hydrology model that's running on the surface and it's providing the infiltration to the groundwater system. It's going through the unsaturated zone and feeding the saturated zone. So all these systems are now working together dynamically. You have groundwater that's being exchanged with the surface water as well, with your rivers and lakes. And so any kind of seasonal changes in the rivers and lake systems are influenced by changes in the groundwater system. So by doing this, we have a fully integrated hydrologic model where we're internalizing those traditional boundary conditions like recharge and infiltration in the groundwater system. So those things that used to be boundary conditions or inputs that we would adjust or calibrate, they're now internalized into the model. It's a full feedback system. We have infiltration, it provides groundwater. If we have high groundwater table, then we have discharge from the groundwater system into our surface water bodies. So this moves the boundaries further away from the processes of interest. So the benefits of this in terms of model calibration is we have more parameters to calibrate against. And that, from a timing and budgetary perspective, it makes it a bit of a longer process, but the end result is a model that is fully integrated and reliable. So we're no longer saying, yeah, we're just going to adjust these infiltration parameters in our hydrology model until we get the fit that we want without any concern about how much water the groundwater system can support, or we're not going to say, well, we're going to assume we have X amount of recharge to our groundwater system to get those water levels where we need them to be, without any concern about, well, how much water do we need to keep our river system running the way it should be. So all these things now need to make sense together, so we can have snowpack measurements, groundwater level measurements, stream flow measurements, and even groundwater quality or stream flow quality measurements. And they all have to work together, and they all have to make sense together. These are all quantitative model calibration parameters that we can measure. We also have qualitative model calibration. Okay, and in this example here, this is a small subwatershed that we modeled in Mike Shee. It's a Mill Creek conservation, or Mill Creek subwatershed here in Cambridge, Ontario, where I'm from. And we can see here, just by looking at this, this is an output from Mike Shee showing this is where we have groundwater discharge to the surface. And so we see here this dark blue line. This is where we have high rates of groundwater discharge to the surface. And this matches actually very, very well with the delineation of where we know Mill Creek is. So this is it's not a line that we've drawn, it's not a delineation of a creek, it's where we have high groundwater discharge to the surface, which matches quite well with where we would expect to have discharge adjacent to a creek. High water levels adjacent to a creek, it flows into the creek and provides that base flow for the year-long flows in that creek. So just qualitatively looking at the results here, they make good sense. And if we look a little closer, obviously we have high discharge along the creek here, where we know the creek is. We also have discharge adjacent to the creek, and if we look at that in another way, we look at the saturation values of the soil in the unsaturated zone. We can see here that high saturation values match very well with the known locations of wetlands. So the green lines here, they indicate the mapped location of where we know we have wetlands. And so those actually match very well with the high saturation values in April for this model. You can also get a qualitative representation of, yes, what we're seeing from the model makes a lot of sense. So the benefits of an integrated hydrology model are that we have this inherent consistency between the modeled surface and subsurface systems. It results in a more robust solution because it uses all the available data that we have for calibration. And it results in a more reliable model for predictive scenarios involving water budgets, potential modifications to land use, evaluating the impact of climate change, looking at groundwater utilization and possible impacts on surface water and wetland, and looking at river system operations and how those might impact groundwater systems. So this it also promotes a better understanding of all the hydrologic processes and their interdependencies. So you're not running these hydrology models or these groundwater models or these river hydraulics models in isolation. They're all running together, and they all depend on the other for inputs and for outputs. So again, some typical applications. Johannes already went over it, but just quickly again, looking at wetland management, conjunctive water utilization, climate change impacts, land use change analysis. I mean, you can't look at climate change impacts on groundwater supplies without looking at the surface. I mean, the surface, what's happening on the surface is affecting what's happening in the subsurface. And so you can't just make some broad stroke assumptions about how much more or less recharge you're going to get due to climate change. You need to simulate those processes on the surface with surface hydrology, and see what makes sense in terms of getting infiltration into the groundwater system or more discharge from the groundwater system to the surface water system. Irrigation management is another big use of Mike Shee in Florida. Drought and flood planning, urban drainage in some special cases, and then environmental river flows. So basically, it answers how and where does all that water flow, and when it gets there, what will it be like? What's going to be the water quality? So with Mike Shee, we have a tool that gives you the ability to simulate all these processes together. So this is a kind of a common schematic that if you've ever seen a Mike Shee presentation, you've probably seen this schematic before. And it just shows all the different processes that Mike Shee represents and how it represents those processes. So the main inputs are precipitation and temperature, and they drive snow accumulation and snow melt. Vegetation-based evapotranspiration and infiltration. So spatially distributed representation of vegetation and soil types. Unsaturated groundwater flow, saturated groundwater flow, river channel flow using the fully hydrodynamic solutions, overland runoff, surface flow and flooding, and then demand-driven irrigation, and you can have integrated water quality across all those processes. So some of the benefits of MikeShe are that it supports grid-independent data input and integration with GIS data sets. So you're not reliant on, or you don't have to have your inputs in the same resolution or the same scale, or the same temporal time step variation as what you're going to model it at. MikeShe handles conversion of data from GIS into gridded data. It handles conversion of different grid sizes into the model format. It handles different spatial and temporal resolutions for input data. It has custom and adaptive solution time steps for each hydrologic process. And this is a really key and unique thing about MikeShe, is that all these different processes are solved at different time steps because they all have different different timing components. Groundwater moves a lot slower than a river system, so you don't need to solve a groundwater system at 5-minute intervals. You can solve it at 6-hour or 12-hour intervals. And so you're really optimizing the solution speed by having these things solved at different time steps, but then exchanging water at fixed time intervals. We also have the advantage of having rigorous and simplified process descriptions for each hydrologic process. So, for example, in the groundwater system, you can have a fully 3D multi-layer groundwater system that gives you really detailed representation of the flows and drawdowns and discharge and changes in water levels in many different layers. Or you can have a simplified representation of the groundwater system using a linear reservoir kind of lumped parameter approach. It'll still give you the ability to track the volume of water that goes into the groundwater system and the volume of water that is discharged into your surface water system, but just a much simpler and less computationally expensive approach. The time-varying soil properties to accommodate winter hydrology, probably not a big concern in Australia, but if you do have concerns about frozen soils, accommodate that. And then we also have time-varying vegetation and surface roughness to accommodate seasonal changes as well as land use changes throughout the simulation period. So looking at urbanized areas or changes in land use over time, you can accommodate that in MikeShe. And then there's support for OpenMI integration with other models or processes. So we also introduced recently Python scripting that allows you to introduce and interrupt the MikeShe solution process and to put in your own processes in there, whether you like a different snow melt routine or things like that. So if I come back to revisit those barriers that I talked about previously with science, data, and computers, I'd say we don't have any of those barriers now. The science is well understood. We're using groundwater models, we're using river hydraulics models, we're using hydrology models on a daily basis. It's a very common engineering practice to use these things to solve problems. So it's not a matter that we don't know how to do it. It's a matter of who knows how to do it. The problems that we have with integrated modeling and why it's not really caught on as much is because we have this narrow expertise of users and they have this inertia with the tools that they're used to using. So the groundwater people, they like their groundwater model tools and they kind of like the way that they've done and handled surface water inputs for so long. They don't really know a lot about surface hydrology. They know a lot about groundwater hydrogeology. Institutional barriers. A lot of government agencies, they'll have their groundwater group, their hydrology group, and the river hydraulics group, and oftentimes they're not even in the same building. So there's government agencies, educational institutions, they all kind of divide up their sciences in that way. And it's getting better, and they're starting to pull together, but it's a long road. And then the scope and the budget of projects. Obviously, if you're just doing a hydrology study, and not every project needs a fully integrated approach, but if you do think that the project could be scalable, and it can be expanded to look at other factors if you're doing a hydrology study, and maybe you want to look at river hydraulics as well, or groundwater impacts, or climate change impacts on groundwater supplies, or climate change impacts on base flows and river systems. These are things that you can expand a study into with an integrated model. All right, so this is a model that been kind of early stages helping a client out with. So it's a surface hydrology model right now. It has an unsaturated zone component, but it doesn't have a saturated zone component. So this is the kind of the startup screen here of Mike Shee. And so, of course, one of the first things you do is you have to specify what it is that you want to simulate. And as I mentioned before, you can pick and choose which processes that you want to include and how rigorous you want to simulate those processes. So in this case here, we have a model where we want to simulate overland flow using a finite difference diffusive wave approximation of overland flow, or it could be kind of more of a lumped parameter catchment-based overland flow. We've said that we want to simulate the rivers and lakes using a hydrodynamic model. So we have a separate model that represents the one-dimensional river system. We have unsaturated flow that we want to represent here using a two-layer unsaturated zone approach. We could have equally easily have done a Richards equation. So it's a fully rigorous one-dimensional Richards equation or gravity flow. And so something just to point out about Mike Shee is that the unsaturated zone that basically connects the surface to the saturated zone, it's represented as a one-dimensional column for every grid cell in your model domain. So it's not a three-dimensional unsaturated zone model, but rather it's a one-dimensional model that assumes just vertical movement straight down from the surface to the saturated zone. That obviously speeds up the simulation time quite a bit, and but it does have some limitations in terms of being able to simulate, lateral flow or perched water tables and things like that. Evapotranspiration is something that we're going to simulate here, and then we're going to ignore saturated groundwater flow in this case. It's still early stages for this particular project, so that's being added at a later stage. So with this here, we have our processes, and depending on what we select here, we're going to be prompted for different types of data in the data tree over here on the left-hand side. And just to kind of show you how that works, if I was to say, okay, well, maybe I do want to look at saturated groundwater flow, I turn this on here, and then my data tree over here will change, and I'll get some additional branches here indicating that it wants me to put information in from a saturated zone. So now I have saturated zone inputs that I need to define, but I'll just turn that off because I don't have any. All right, so we have the simulation specification. We have the simulation period here when we want to run it from. In this case here, it's a 7-year simulation from 1971 to 1978. We have time step controls. So here we have the time step controls for each one of our processes. And so we have the maximum allowed time step for overland flow, which is 2 hours. Maximum allowed time step for the unsaturated zone flow is 2 hours. And then the, let's see, the incremental here rate for increasing time steps or decreasing time steps is 0.5. And then we have this one here, which is kind of cool. One of the big issues that a lot of integrated models face is time steps and making sure that they're able to represent meaningful rainfall events and the hydrologic response from those events. And so if your time step is too big, you may miss a highly intense rainfall event. And we all know that 25 millimeters of rain over 1 hour has a much different hydrologic response than 25 millimeters of rain over 2 days. And so you want to be able to run the simulation at a time step that solves fast enough and doesn't take too long. But you also want to build in some safeguards that say, well, I don't want to miss that big rainfall event, and assume that it's going to be, falling over 6 hours rather than falling over 15 minutes. So what we do here is we have this value here that we can specify that says, okay, if I get 40 millimeters of rain within, my time step, my overland flow or my unsaturated zone time step, it's going to introduce a new time step. So it won't allow you to have this super intense rainfall event and spread it over too long of a time period without introducing a new time step. So that ensures that you're getting a very good and accurate hydrologic response. Okay, so I'll skip over the computational parameters here. So here in the model domain, this is where you specify the area that you want to simulate, so the boundaries of your watershed. And you can do that with a shapefile. And then you specify the number of grid cells in the X direction, number of grid cells in the Y direction, and the cell size. And you can specify your map projection as well. So this is a pretty big model, 575 by 725 grid cells. Each grid cell is 300 meters. So it's a very large study area in this case here. I don't have the exact count of the square kilometers, but I'm sure it's certainly between 50 and 100,000 square kilometers, I believe. So once we've defined the domain of the model, we need to provide it with topography data. In this case here, we have a number of different formats that we can use. A DFS2 file is a DHI file structure. That's what the DFS stands for, DHI file structure. And then 2 indicates that it's a 2-dimensional gridded format. So it could be 2-dimensional gridded static or 2-dimensional gridded time series, but topography is typically just a static value. We could also use a point theme shapefile or an XYZ ASCII file. So that gives us our topography for our study area. And then we need climate information. So in this case here, it's a project for a study site in Alberta. So it includes snow melts, and in that snow melt routine also includes melting due to shortwave solar radiation. We have precipitation correction for elevation and air temperature correction for elevation. So in our precipitation rates, we have in the study area here, we have all these townships, and the province of Alberta provides precipitation time series for each one of these townships. And so this is based on interpolations and treatment of the rainfall gauges that are available throughout the province. So they create these time series for each township. And so we have one time series for each township. So if I click on these values here, you can see this red square indicates this is the township that's associated with this time series. And you can see the time series here across the top for the study period. So then clicking on different items here just shows us different squares here where the townships are located. So we have that for precipitation rate, and then for reference evapotranspiration, rather than doing it for each township, that just divided the study area up into 3 different zones here, north, central, and south. And so there's a different potential evapotranspiration or reference evapotranspiration value or time series for each one of these zones. And so this here is the evapotranspiration that will try to be achieved by the model. So it's going to try to remove this moisture from the surface of the model if possible. So again, this is the reference evapotranspiration that you would get, on a typical well-watered grassy soil or something like that. We have solar radiation, also provided as time series for the north, central, and south areas, and then air temperature according to the townships. So we have highly detailed data where it's available, and then some more lumping where we don't have that kind of data available. And then for the snow melt, it's a degree day coefficient method. So we have melting temperature. What is the temperature that the snow melts at? And this here can be, interestingly enough, it's a static value that they've used initially here, but you can also have a time series value, and it can be spatially distributed as well. And the usefulness of that is that you can say, well, if we have forested areas, Mike Sheet doesn't allow you to specifically account for forested areas versus open fields. And so you can set your melting temperature to be different for different coverages. Likewise, for the degree day coefficient, in this case here, they divided the degree day coefficient up into different zones. And here we have a constant value for this is the amount of water that's released per degree of Celsius per day. That can be, again, a constant value for the zone. It can also be a time series. And in the Okanagan project, we used a time series of degree day melting coefficients to account for different seasonal effects. So in the dead of winter in January, 3 days of unusually high temperatures won't produce a massive amount of flooding because the snow is not really that ripe at that time of year. Whereas if you had elevated temperatures in say March or April, then you'd get a much bigger response. And so we had a degree day coefficient that was higher in March, April than it was in January, February. So that just helps you account for factors like snow ripening. Okay, then we have land use. So here we have vegetation. So we have a map of vegetation distributions throughout the area. So each one of these colors represents a different code number, and each one of these code numbers is associated with a different type of land use. You can see here a listing of all the different types of land uses. And each one of these, if I look at, say, coniferous forest, for instance, I'll see these are all the grid cells here in red that we have identified as coniferous forest. And then for each one of these here, I have a leaf area index indicating what is the area occupied by leaves throughout the year. So of course it gets larger in the summer months and falls off in the winter months. And then we have rooting depth as well. So again, for each one of these here, we have number of grid cells and areas in red that indicate where we have, again, agricultural areas, and what is the leaf area index and rooting depth for each one of these grid cells. We have a rivers and lakes model. So this model was developed using Mike 11. So Mike 11 is the one-dimensional river hydrodynamic model that DHI develops. So if I click on that, I can go to my Mike 11 editor here, and I can see this is my river network. And it's a big model, so it takes a bit to load up here. So it's a very detailed model, lots of cross sections throughout. I won't spend a whole lot of time looking at the Mike 11 model. Just to show you that you can get in here and you have a full-featured editor here for looking at and building a one-dimensional river system model. All right, and then for overland flow, we have Manning's roughness values. So we have different land use types describing different roughness values. So we have a range of values here from 5 to 75, and these are Manning's M values. I'm not sure what the standard is in Australia. Here in North America, we typically use Manning's N, so it's in the range of like 0.03 to 0.08. But Mike Shee kind of defaults to Manning's M. You can change it if you want. But in this case here, they just went with Manning's M. And then detention storage, initial water depth. Anytime we load a map here, it's a huge file. So initial water depths here, we have some lakes scattered throughout the system here. So we have some initial water depth in those lakes. Then we have a surface subsurface leakage coefficient. And in Alberta, in the northern areas here, it's important to be able to account for frozen soil. And so in these cases here, they have accounted for that with lower leakage values. And then finally, in the unsaturated zone, we're using a two-layer unsaturated zone model here. And so we can see here we have a range of different soil types. And for each one of these soil types, we have a set of parameters that describe the unsaturated zone soil type here. So we have water content at saturation, field capacity, wilting point, saturated hydraulic conductivity, and soil suction at the wetting front. And then if you want, you can also include bypass constants to be able to bypass the unsaturated zone and transfer water directly or a portion of the water directly from the surface to the saturated zone. In this case here, we don't have a saturated zone model, so it's not terribly relevant. Okay, so that should give you some idea of the inputs that are required. So in this case here, we have unsaturated zone soil descriptions. We have Manning's roughness values for overland flow. Detention storage, I didn't really talk much about that, but that's just, detention storage is the depth of water that kind of collects on the surface that needs to be filled before you start to see overland flow. And that really just allows you to account for the fact that here we have grid cells that are 300 meters by 300 meters. And of course, you're not going to capture all the little depressions and puddles and things that form in that size of a grid cell with the overland flow. So there's going to be some water that collects in different places and gets stored there as a detention storage before it starts to release overland flow. And so that's what that detention storage allows you to account for. So in this case, it's a huge model. I'm not going to run it live here, but it has been run already before. And so we have some results that we can show you. All right, so here what I have is a map of depth of overland water. And I've taken a couple of example cross sections in my river system model, and I've shown them here. So you can animate this as well. So if I wanted to see what this looks like over time, I'm currently going at 24-hour time steps. And I'm not sure how well it's coming across on your screens there, but you can see the water levels in the river system are kind of moving around a bit. And we have maybe a rainfall event occurring. Depth of water in the overland gets deeper, and then it gradually subsides. All right, and then we also have another tool. This is a result viewer tool that's used in Mike Shi. And we also have another tool called Mike View, and it's more for looking at the detailed analysis of the river system model. And so this is what we have here. So I've taken a view here of the one-dimensional river network. I've drawn a profile along the main river stem here. So we can see here, this is the water in the profile. And this is down here, a time series at one of the chainages along the river system. And so if we want to animate that or see what it looks like at different times, we can just march through here. We can see that the water level in our profile here changes with time. During big rainfall events, we get higher discharge in our river system. Yeah, so this is just, again, over on the left-hand side here, it's a map showing the river network. And if I zoom in here, you can see it's got flow direction arrows for the way it was digitized. And then we have a profile here. So this is a profile along the river system from high to low here. And then we have a time series of discharge in the river as well. So just if we march along here at different times of the year, we can see we have synchronized water levels in the river profile. And we can zoom in and get a closer view of that. And we can animate it as well. All right, so that's kind of, I guess we're right about at the 1 hour mark here, so I don't want to take anybody too far over. But I mean, if there's specific stuff people want to see, I'm happy to stick around and
Oh, that's really
investigate a little bit further.
really fantastic stuff, Patrick. And personally, I just wanted to thank you again. And I've got a much clearer understanding of Mike Shi now as a fully integrated watershed hydrological modeling tool. And thank you very much for everyone for their questions, and Patrick for spending this extra time. I think quite a number of panelists are, attendees are dropping off. Look, are you happy to answer a few more questions, Patrick? You sure it's all good with your time there?
Yeah, that's okay. I got a few more minutes, and I'll send that paper to you as soon as we sign off here, so you can forward that to the participants.
Fantastic, thank you. There's a question from Sakshi. If she's running a model for 10 years, then which year's land use land cover LULC should I choose?
Well, that's a great thing. You don't have to.
Okay.
You can have time varying land use values. So your land use can change with time. You can use a two-dimensional gridded file that has Manning's values that will change with time over the simulation period.
Look, as Patrick mentioned, if you have any technical questions, please direct them to him. And thank you, Patrick, really for the time you spent today, and also for being willing to answer some more future questions. And if anyone would like to learn more about Mike Xu or undergo some training, or perhaps if they're ready to take the next step and start using Mike Xu, then please contact me. You can see both Patrick and my emails on the screen. And as mentioned, you'll be receiving an email from me in the next few days with a recording, and you can feel free to communicate with me via that. Again, Patrick, really thank you for your time. It's probably well over 7 p.m. now in Vancouver. Is that correct?
Yeah. Hey, one last thing, if there is anybody still on there, that I'd just like to point out that a formula that's worked really well for us here in Canada anyways is that when people do have a project, I mean, it is a pretty complex tool. Not a lot of, companies have, people who are capable of handling all these processes together. And a formula that's worked really well for us is that if somebody does have a project where it's applicable, what we do is team up with them and basically guide them through the process on the first project or two. And eventually they learn and they don't need us anymore. But it's just been a good way to kind of have that comfort level from the client and from the consultant that, they're not going to be struggling or doing things in a wrong direction for too long.
I think that's really great. I think especially having that service, as you say, it's especially for someone like me with very little hydrologic experience, it does look like a powerful tool, but obviously quite a steep learning curve.
Yeah, for sure.
Fantastic. Well, again, thank you so much, and thank you everyone for joining us today, wherever you may be and whatever time it is. I'd like to say goodbye, and I hope you can join us again in the future for some other webinars.